we're asked to do two things with respect to this sum. We're supposed to show that the sum from 1 to infinity of minus 1 to the n plus 1 over n squared converges. That's going to be a very easy task. And then we're asked to approximate the sum. So I think the first thing anyone ever would notice about this sum probably is that it alternates. And so maybe you think to use the alternating series test to show that it converges. That would be fine, and it certainly does. The formula for use of n is 1 over n squared. Those are always positive. If I compare the n plus first term to the nth term, well, that one's definitely smaller because the bottom of the fraction got larger. And then finally, the limit as n approaches infinity of 1 over n squared is certainly 0. The alternating series test guarantees me this converges, but we could actually do this easier. If I if I just take the absolute value of the series, I get the sum of the reciprocal squares. That's a convergent p-series. So not only does this series converge, it converges absolutely. So when I take the absolute value of each term, I get the sum of the reciprocal squares. So whether we want to use the alternating series test or just the test for absolute convergence, we know this series converges. Now we're supposed to approximate the sum, and well, the easiest way to do that is to find a partial sum. What's nice about this being alternating is we're able to get a bound on how far off we are from the actual value we're converging to. I'm actually going to find the 10th partial sum as my approximation. So I plug in a 1 and well, I'll get out a 1. Next I'll have a minus 1/4. I'll just continue adding and subtracting reciprocal squares as they come up. And then finally, minus 1 over 10 squared is 100. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms. And earlier in the day, I did use my handy TI-84 to add those together and to find out that this was about 0.81796 rounded to that fifth decimal place. All right, so this is an approximation for the sum is converging to somewhere around that, but then the natural question is, how far off are we? Well, we have a nice theorem about alternating series and the remainder. The alternating series estimation theorem says that the first unused value of u gives me a bound for my error. Well, that would be 1 over 11 squared is 121. If I was to take the actual sum and subtract s sub 10, I know that that difference is less than 1 over 121, or about 0.008. So I'm pretty sure that I'm close to my actual value. So I've approximated the sum. I even have a bound on my error. But just for fun, I want to recall that in class and all over the internet, we can find out that the sum of the reciprocal squares is actually pi squared over 6. And I'm not going to show why that is in this video, but we're just going to take that as a fact. This is a known fact that many folks have established. And let's look at what pi squared over 6 is approximately. We get about 1.64493 and some more stuff. And then I see my approximation here, and I say, my approximation is not far off of half of that amount, and that seems, well, at least a little interesting. And so I'm just going to say that if I take this series, which converges absolutely, and I subtract off just the even values. So that would be like taking the series that looks like this but doesn't alternate and just erasing the even ones, right? 2 times n squared. Well, I'd get a number. Well, I'd get 1 plus a 9th plus a 25th plus 1/49th, right? I'd get that. Well, if I double that, now it's like I took away the even ones and took them away one more, making them all negative. I'd get this series. I'd get this one as if it was going out. Now, it's important that both of these series converge absolutely, because the rearrangement theorem for absolutely convergent series applies and tells me that all the arithmetic I'm doing here is okay, and that I get the same sum no matter how I add these numbers together. All right, so I get n equals 1 to infinity of 1 over n squared, but here I have a 2 and this sum, but on the bottom I could rewrite that as a 4 times n squared. Well, the 1/4 is a constant, I could factor it out. And that would be a 2 over 4, which is a 1/2, and then the sum of the reciprocal squares. Well, if I take a number and take away half that number, I'm left, well, with half of it. So this series converges to, well, half of the other, pi squared over 12. So there was my estimation. Pi squared over 12 is about 0.8224, 1, 2, 3, 4, 5 decimal places, and we'll round that to 7. And if I subtract these two, I get 0.004, which is less than the 0.008 I was promised. And so there we have it. We've done the two things, and we've also explored now enough to know where this converges to. Well, that is, if we believe that the sum of the reciprocal squares really is pi squared over 6.